In Section 6.2, we covered properties of parallelograms, and then we flipped them around in Section 6.3 to show how we prove a quadrilateral is a parallelogram. The next two sections are similar. In this section, Section 6.4, we cover properties of a couple of special parallelograms, and then in the next section, 6.5, we flip them around and show that you can use those properties to prove a parallelogram is one of those special ones. It's the same kind of thing. So let's get to it. A few vocabulary items to get out of the way. The first special parallelogram we are covering is a rhombus. Here is the definition. A rhombus is a parallelogram with four congruent sides. Another way of saying it is, a rhombus is an equilateral parallelogram. This is what it looks like. Please don't call it a diamond. That's just so wrong. Next up, something you are probably familiar with, a rectangle. A rectangle is a parallelogram with four right angles. You could also say a rectangle is an equiangular parallelogram. I'm guessing you have probably seen one or two before. And another one you have probably seen before. A square. A square is a parallelogram with four congruent sides and four right angles. Or you can go with this big mouthful. A square is an equilateral equiangular parallelogram. Phew. Or maybe you prefer a square is a rhombus and a rectangle. In Venn diagram form, it would look like this. And all of this means is that a square is a regular quadrilateral. So many ways to describe the same idea. Pick the one that will help you remember best. Although most of you probably already had a good idea of what a square was. On to the properties. A rhombus has two special properties that we will be looking at. Both of them have to do with the diagonals. So here are 5 different rhombuses with their diagonals drawn in. Do you notice anything in particular about the diagonals? One special property is usually easier to spot than the other for students. The one students usually see first is that no matter how I draw the rhombus, the diagonals are perpendicular. This is that idea written in theorem form. You may notice that like the previous sections, this one doesn't have an official name. It's not a particularly long theorem, so if you have to write it out as a reason and a proof, it wouldn't be too bad. But something like this helps a bit. That's about it for this theorem, though. It isn't that hard. You just have to remember it. Back to these rhombuses. There is a second special property that has to do with the diagonals. It has to do with what the diagonals do to the four angles of the rhombus. It's usually harder for students to see compared to the perpendicular diagonals. But the effect is most dramatic on the red and black one, if you want to try to figure it out before I tell you. If a parallelogram is a rhombus, then each diagonal bisects a pair of opposite angles. Now in every parallelogram the opposite angles are congruent, but this theorem tells us that the diagonals also bisect those opposite angles. It is very common for students to try to make rectangles or other parallelograms bisect those angles, but it is only true for rhombuses. Just watch out for that. Students do it all the time. This theorem doesn't have a name either, and it doesn't abbreviate very nicely, but you don't use it very often in a proof, so it won't be too bad. This theorem brings us to this very handy thing to remember. The opposite angles are congruent, and this theorem says that they are bisected like this. And previously we had a theorem that said that the diagonals are perpendicular. There are 12 angles inside this rhombus. It is very handy to remember that there are 3 sets, each with 4 congruent angles. When you are solving problems involving rhombuses, it is very useful to remember that the angles come in congruent sets like this. It will help you quickly fill in all of the missing pieces. Now we move on to the special property of a rectangle. Like the rhombuses, the special property of the rectangles has to do with the diagonals, which is why I have drawn them in here. Do you notice anything about them? The diagonals clearly aren't perpendicular. Just look at that green one. The diagonals don't bisect the angles. It may look like it on the purple one, but once again the green one really shows that they don't. Have you figured it out yet? Both diagonals in every rectangle are the same size. This is that idea in theorem form. If a parallelogram is a rectangle, then its diagonals are congruent. Once again, this theorem has no name, but it only comes up rarely in proofs, so the abbreviation isn't that crucial. Something like this is doable. Now just like the last rhombus theorem, there is something that is very handy to remember with these rectangles. Since the diagonals are congruent, plus this is a parallelogram where the diagonals bisect each other, that means we have this. In a rectangle, those 4 line segments are all the same length. As a hint, this forms 4 isosceles triangles, and math books and math teachers often build and or ask questions that involve isosceles triangle skills when dealing with rectangles. Now we come to a square. Squares have a lot of properties, which may seem intimidating, but none of them are new. Remember that a square is a parallelogram, a rhombus, and a rectangle. Due to that, the square has all of the properties of all those things. A square has all of the properties of a parallelogram. None of these should be a surprise. None of these are new. A square also has the 2 special properties of a rhombus, and also the 1 special property of a rectangle. None of these are new properties. There are just so many of them because a square is so many things. The good news is that none of them are new, and a square doesn't have a new special property all to itself that you need to know.